Boosting is another ensemble model. What was the first ensemble model that we discussed previously? We
Random
discussed an
forest.
ensemble
Random
model called
forest.
random forest. Whenever you hear the term ensemble, you have to imagine that we start gathering several models, we build several models, and then somehow we combine them. By doing so, we can improve the accuracy by a little bit. Usually that little bit is 2 to 3% lift on the accuracy on whatever given data is. Boosting is also another ensemble model. Here also we build several models and combine them. That will improve the accuracy. But only thing is boosting uses a totally different theory. Random forest uses a totally different theory. Let us see what is the theory of boosting and how do you apply it on a given data set to solve a problem. The theory of boosting, the idea of boosting is very, very simple. Boosting is generally known as GBM technique, gradient boosting method. Now here is the actual theory of GBM or boosting method. Very, very simple concept, but somehow it gives so much better accuracy. It works very effectively. Imagine you have a data set which has X and Y. You have X1, X2, X3, and so on, XK variables, features, and then the target variable Y. What do we generally do? We try to build a model. Let's say f of X is the model. We try to build a model that will make a prediction. Obviously, when you are making a prediction, you will make some error. So when you're predicting Y value, this is the result given by the model. This is a predicted value, and this is the error given by that particular model. Usually what we do is we tend to finalize this model. We tend to build best of the bestest model in one shot or in multiple iterations. And we tend to finalize this. This is where boosting differs. Boosting tells us, focus on this everyone. Boosting tells us that do not worry about building the best model in one shot. No, don't build the best machine learning model in one go. Don't do that. Build a moderately good model. Build a model that simply beats a tossing of the coin. When you toss a coin and predict whether a customer is good or bad, you'll be 50% accurate. Build a model that is slightly better than that. That's it. Build a moderately good model. Let there be error. No problem with that. So you have X, you have Y. This is f of X result. These are the results. And then let there be error. No problem. So what boosting tells you is, if you think there is some error here, if you think there is some pattern left over in the error, if you think this error can also be modeled, then what you can do is try to take X as input. This time take error as output. If you feel this pattern, try to model for the error. So how do you model for the error? Try to predict error. That model will be, let's say, some h of X, and then whatever is the leftover error. So you have X. Now the target variable now would be error 1, whatever is this error here, error 1. And this is the h of X result, whatever is the leftover error. So your final target variable Y will be f of X first model result plus error 1. But error 1 has been modeled because error 1 has some pattern h of X plus error 2. That is the main seed idea of boosting. What is it? Try not to build one model and just stop there. Try to build multiple moderately good models, combine their result. Surprisingly, that works much, much better than simply building one strong model. Once again, let us look at it from the data example point of view. Look at this. You have X versus Y. This is the data. You build the first model, Y equal to some f of X plus some error. This is X, this is Y. These are the f of X results. And this is error. If you feel this error is really high, if you feel the model has the scope for learning these patterns as well, and somehow this model could not capture that, then we don't need to worry about that. What do? You try to build a model for the error equal to some h of X plus error 2. That means you take this X as it is as input. This error is the output. Look at that. And this is the h of X result. Now this is the leftover error, error 2. Your final output will be Y equal to f of X plus h of X error 2, leftover error. Definitely this error will be less than the previous error. What if this error is also high? What if there is some pattern in this one as well? Can you think what will be our next step? What is this error is also high? What will you do next?
Sir, build another model.
Build another model. Perfect. What do? You try to build g of X plus some leftover error, error 3. What if this is also high? What if there's some pattern in this as well? What if this also, we can squeeze some pattern? Then what do?
Keep on iterating.
Again, do it like k of X plus error 4. The analogy of this is, have you ever seen that ganne ka ras, the sugarcane juice, right? What happens? First they put one sugarcane. Yes or no? Then they get some juice out of it. Are they going to throw it away right after that first iteration? No. Again, take that, put it back. Then second set of whatever is a leftover juice that will come. That's when we feel that it's better that they should throw away. Are they going to do that? I think you have experienced it, right? Again, the same set will be taken again. That will be kept in the machine. This process is continued until unless the last bit of juice is squeezed out of that sugarcane. Exactly the same way the last bit of pattern is squeezed. Until then, we keep on repeating the model. Again, for error 4, you build t of x plus error 5. Again, for error 5, you build some k of x or some b of x plus error 6. You keep on doing it. Tell me, what is the theoretical stopping point if you keep on doing it? Build a model for the error, reduce it, build a model for the error, reduce it. If you keep on doing it, what's the theoretical stopping point? Where do you stop? When do you stop this? Theoretically, may not be practically. Yeah.
Error becomes 0.
Theoretical stopping point is when the error becomes 0. That's right. When the error becomes 0, that's when you stop. But generally, are we really happy when we see an error of 0? Or suddenly we think of something? What do we think of whenever you see error equal to 0? Generally, what is the first thing that comes to our mind?
Accuracy is 100%.
Error is 0, that means accuracy is 100%. What does that generally lead to most often? Whenever we see an error of 0, mostly that is leading to
Good model.
Overfitting.
Usually that
Overfitting.
leads to overfitting, isn't it? Because you tend to
Yes,
build the
sir.
model on the trained data. Yes or no? On the trained data, you have done until a point where you kept on building the model for the error, building the model for the error. You made the error 0. There's a high chance that yes, it is a good model on the trained data, but it may not validate well. So it leads to overfitting. That is why you cannot overdo it. You cannot keep on reducing the error. So the number of iterations, this is every model is result from one iteration. The number of iterations is a hyperparameter here. So how many iterations shall we run? That need to be decided carefully. Let us suppose you have to run for exactly 8 iterations, but you have executed boosting for 20 iterations. What will happen in that case? If you have executed boosting for 20 iterations instead of 8, are you going to get an error from Python or the model will be built?
Sir, the model will be built.
The model will be built. But what will be the problem with that model?
Overfitted.
That model will be overfitted. Suppose that you had to build 8 models, but you have actually collated only 2 weak models. That's it. You stopped at 2 iterations only. Then what will happen?
Underfitting.
The model will underfit. So if you run fewer iterations, then model will be underfitted. If you run too many iterations, then the model will be overfitted. The number of iterations have to be optimal, neither too high nor too low. Finding out number of iteration optimal value is not a very difficult task. It's damn easy. And we will find we have different methodologies to find it. It's not that hard. So one of the hyperparameter is number of iterations, and it cannot be too high, it cannot be too low. When we are going to do the case study later on, then we will see how to find out the optimal value as well. Once again, go through the theory of boosting. How does that work? Imagine these are your initial data points, x1, y1, x2, y2, x3, y3, and so on. You try to take x as input, y as output. So you build a model f of x. So while you're predicting y, your result will be f of x plus whatever is leftover error. Then next time your data points will be x1 error 1, x2 error 2, x3 error 3, and so on. These are the data points. Try to build a model for this scenario. So that will be y equal to f of x plus the second model is h of x plus whatever is leftover error. Then again build the model for this, unless until you get the least error. That's the theory of boosting. There is one practical factor that has been included in this theory. Listen to me carefully. What's that practical factor? Usually you have to take h of x as it is. Instead of taking h of x directly, we multiply that with rho in real life. Multiply h of x with rho, and rho is a number that is between 0.1 to 0.0001. Let me put it this way, 0.0001 to 0.1. Usually by default, rho is taken as 0.1, and that works for most of the cases. What does that mean? If h of x is equal to 20, h of x predicted value is 20, rho equal to 0.1, are we really going to take 20 into the model? No, we will multiply that with 20, 0.1 into 20, we will take only 2. In the place of 20, you're considering only 2. That means the error will not be reduced that much. There will be still very high error left over. That will prolong the algorithm. That prolonging is important. This rho is known as shrinkage or learning rate. You tend to hear at least one interview question. If somebody is testing you on boosting, there will be a question on this shrinkage or learning rate. Let us look at it carefully. What's the need of it and all that. Once again, how does that shrinkage or learning rate work? The original equation is y equal to f of x plus h of x plus error 2. Instead of taking h of x as it is, you multiply that with rho. Rho is usually a number between 0.0001 to 0.1. By default, it is taken as 0.1 in many tools. For example, if h of x prediction is 35 and rho is 0.1, am I going to take 35 as it is? No. What is the final number that will go here? 3.5 only. That means the error will not be reducing drastically. Error will still reduce, but it will not reduce drastically. It will reduce only by a little bit of amount. That means your algorithm will run for multiple iterations, and running this algorithm for multiple iterations is necessary. important. Let me prove why running multiple iterations is important. Even before that, let us see the impact of row once again using a different example. This is your original scenario, right? We have already seen it, x versus y. And then you build the first model f of x. This is the leftover error. And then you build the second model h of x. What are the predicted values of h of x? These are the ones. Tell me, if I introduce row here, row equal to 0.1. Instead of 12 over here, what will be the number that we will have here? Instead of 12, it will be 1.2. That will be minus 4.5. That will be minus 3.2. Do you think the error will reduce from 10 to 2, 40 to 5, 30 to 2 in one shot like this right now? If you have
No,
introduced
sir.
row? No. So this is the new h of x value. Error earlier, it has reduced from 10 to 2 in one shot, 10 to minus 2, minus 40 to 5 in one shot, 30 to 2 in one shot. But here from 10 to 8.8, then later to somewhere around 7 or 6, then 5, 4, 3. After a lot of iterations, it will reach this number. Earlier, it has reduced from 40 to 5 within one shot. Now it is reaching from 40 to 35, then 30, then 20, then 25, like that. It will take multiple iterations to reach that number. Can you make a guess roughly? Previously, without row, whatever error has reduced in one shot. To reach the same error, how many iterations it may take? We are taking row as 0.1. We are taking only 1/10 of every value. So roughly how many iterations will it take now to reach the same error? Let's say if I want to reach minus 2 here, if I want to reach 3 here, if I want to reach 2 here, roughly how many iterations will it take?
10.
Roughly?
7 to 10.
Approximately
Yeah.
10.
Approximately 10 iterations it will take, isn't it? Because every time we are taking only 1/10 of it, roughly either 9 or 10 iterations definitely it will take. That means if you are not using row, if you're not using any learning rate, then if your algorithm ends in 8 iterations, with row equal to 0.1, how many iterations you have to run now to reach the same accuracy?
80.
80 iterations. From 8 iterations, you are pushing it up to 80 iterations. Aren't you thinking that you're prolonging the algorithm? Yes, we are prolonging the algorithm. Why are we prolonging the algorithm? Here is the final logic. Look at this. Imagine you're building this boosted model. At the end of every iteration, you have train accuracy, test accuracy. If I ask you this question, how many iterations will you run this algorithm for? What will be your option? How many iterations?
7.
Why can't we run for 9 iterations? What's the problem there?
Sir, overfitting.
Train accuracy is high, test accuracy is significantly low, overfitting. 8 or 9 iterations. This is a zone of overfitting. Why can't we run for 5 iterations? This looks perfect, 65 and 64.
Underfitting. But
Underfitting.
the accuracy is less.
Accuracy
Underfitting.
is less, there's a scope for improvement. So 1, 2, 3, 4, 5, 6 is the zone of underfitting. And 8 and 9 is the zone of overfitting. So the best optimal value that we can think of accuracy is 7. We have 84% accuracy on train data, 84% accuracy on the test data. Super good. We finalize this. Imagine there is another data scientist who is working on the same data set, who is also using the same GBM technique that we are using. But somehow that other data scientist has shown 90% accuracy on train, 90% accuracy on test. Surprising. How come somebody is using the same data set without any change, same technique without any change, same tool Python without any difference? How come he's getting higher accuracy? If you want to increase the accuracy, you have to increase the iterations. Can you increase one more iteration? What happens if you increase one more iteration? What is happening here?
Overfitting.
Overfitting. If you reduce iteration, obviously accuracy won't improve, isn't it? By reducing the iterations, can we improve the accuracy? No way. How to stop at this 90/90 is the question. Now comes the story of learning rate. Look at this carefully. It is suggested in boosting, it is suggested that from step by step, from iteration to iteration, boosting algorithm should not learn quickly. Boosting algorithm should not increase accuracy that quickly. Look at this. Within one iteration from 10 to 15, 15 to 30, 30 to 45, 45 to 65, boosting algorithm from iteration to iteration, it is learning too quickly and it is increasing the accuracy too quickly. If you introduce row, which is 0.1, at the end of 7 iterations, you have 84% accuracy now. If you introduce row, at the end of how many iterations you will have 84% accuracy? Roughly
70.
70. Whatever you achieved in one iteration with row equal to 0.1, how many iterations will it take now?
70.
Like whatever you achieved in one iteration, now it will take 10 iterations,
10 iterations.
20, 30, 40, 50, 60, 70, 80, 90. So earlier you have run for 9 iterations to reach this accuracy. Now you're running 90 iterations. But there is an advantage in this. What is the advantage? Now, if I ask you, can you tell me the number of iterations that I have to run to reach 90% accuracy on train, 90% accuracy on test? roughly where it will be. Can you make a guess? 90%
75.
accuracy on train, 90% accuracy on trace. To reach that, what is the expected number of iterations roughly where you will get it? Roughly
Between 70 80.
Between
somewhere
70
around
to 80.
74 or 75 or 76. That's the spot, isn't it? Much more granular point where you have 90% accuracy on train, 90% accuracy on test. Makes sense. So basically, if you are learning very quickly, in this particular case, there's no way you can give 7.5 iterations. But if you give 75 iterations here, it's almost same as taking 7.5 iterations there, isn't it? That's the reason why learning rate is important. So to answer that interview question, why learning rate is used to slow down the process of learning in boosting. By slowing down the process of learning, we will be able to find that very clear granular point where we have maximum accuracy on train, matching accuracy on test. If we learn too quickly, there's a very high chance that we may miss out that granular point. Maybe one iteration lesser, we will be underfitting slightly. This is slight underfitting. One iteration more, it will be overfitted slightly. So if you want to find the optimal granular point, learning rate is required. You have to slow down. Usually learning rate of 0.1 works for most of the cases. Is the concept of learning rate very clear to all of you? Have you understood what is the need of learning rate?
Yes.
Okay. Now that is GBM, and by nature of GBM, by default, it is asking you to prolong this algorithm. Okay. Now when it is asking you to prolong this algorithm, what is the first issue that you see with boosting? What is the first thing that comes to your mind? When you are using boosting, automatically it is asking you to prolong it and run for multiple iterations. Automatically we expect boosting to be somewhat slow, isn't it? Time consuming. The original package of boosting used to take a lot of time some time back. Then there's a solution came to that. There is a package called XGB. It is known as XGBoost. XGB is a different package which uses boosting theory only, but it's an alternative package, extreme gradient boosting. XGB is the faster version of GBM package. So what did developers of XGBoost do? They have made number of performance enhancements. So XGBoost is a package, GBM is a package in Python, but XGBoost works much faster. So internally the code has been modified for better processor and cache utilization. XGB also supports multi-core processing, and you can use GPU also. That will make it much faster. For example, usually you have CPUs, octa-core CPU in my system. What do you mean by octa-core? You have 8 cores. Each of the core is very strong, very fast, and they take heavy load. But what is GPU? In GPU, you have so many cores. 1024 cores versus 8 cores. But each core will be doing a small arithmetic or mathematical or graphical task. Very small task they will do. But what is the advantage of GPU? Small tasks, max to max, how many parallel processes you can run here? If you are using CPU, parallel, if you want to run in this octa-core, you can run 8 processes. But how many processes you can run parallelly here? Nearly
1024.
1024. So if you have smaller calculations, obviously these mathematical calculations are very easy for a system. If you have simple calculations, you can actually run a lot of calculations parallelly. That will make it much faster. So if I have to tell you from my experience, let's say somewhere in 2015, 8 or 9 years back, if we use GBM package for a data set, which is roughly having around 0.5 million rows, okay, somewhere around 5 lakh rows and few columns, GBM used to take around roughly around 90 minutes, which is like 1.5 hours of processing time. And XGB used to take around half or less than half of it, around 30 minutes of processing time. This is 90 minutes. This used to take 90 minutes. This used to take 30 minutes. XGB with extra hardware GPU, that used to take around 2 minutes. 90 minutes to 2 minutes is a huge difference, isn't it? But fast forward to 2022, same problem statement, GBM, since our systems got better, isn't it? We have better processors in our system. So GBM package itself is taking not that much time, 5 minutes it will take max. XGB will take 2 minutes. XGB with the GPU extra soft hardware, that will take around 10 seconds. Now 5 minutes is not a very big deal. People don't care about this 5 minutes. Model building may take time. Model prediction will be faster only anyway. So 5 minutes to 10 seconds, people don't really care. So previously XGB was given a lot of preference, XGB package. Nowadays, even you can use GBM or XGB, any of these two. Okay. when you join a company, when you're working on a problem statement, there's a high chance that you will be using XGB package. Okay. We'll be doing the exercise on both of them. That is the theory of boosting. Once we discuss some questions on this, we will go to the application. We will see one case study, how boosting can be applied. Let's say, compared to a decision tree, you compare it to a random forest. Random forest will give you 2 to 3% lift in the accuracy. Boosting, how much will be the accuracy? Around 2 to 3% lift in the accuracy. Random forest is a black box method. It's very difficult to explain what happens inside. You cannot draw it. How about boosting? Is it easy to interpret, or it is a black box method? Is it easy to draw? Boosting is also a black box method. What happens inside, very difficult to see. Random forest is calculation intensive. Boosting is also calculation intensive. Random forest is time consuming. Boosting is also time consuming. Random forest is not that easy to interpret. You cannot interpret the results easily, which is black box. Boosting also you cannot interpret. Interpretation you cannot. So on a wide variety of parameters, if you see, random forest is almost equivalent to boosting, almost. Only advantage boosting has is boosting has a package called XGB. Somehow that makes the programming much faster. So that is why boosting is kind of crowd favorite. Otherwise, theory wise, both of them are almost equal. You can use any one of those two in for a given situation, but boosting has a better package that makes our processing much faster. Are you ready for the case study? Yeah.
Yes, sir.
Yes, sir.
This video has been shared by Flipkart. So basically, this is one of the warehouse in the outskirts of Bangalore. There's a place called Jigini beyond Electronic City. In that, they have this warehouse. In that warehouse, these small bots that you see, they're automatically doing the product sorting and pushing it to the exact place where they need to be delivered. So Venkat, just like me, he used to be an operator. Earlier, he has to do a lot of work manually. Now these small bots, there's a machine learning model inside each of these bots. Automatically, they're finding out what product is it and where it need to be pushed. A similar example to this would be this one. Here, different types of garbage is going on this particular conveyor belt. Now these robotic hands, they have one machine learning model inside them. They are automatically classifying what exactly is this. Let us, this is fiber, this is a water bottle and all that. And then product classification is happening here. We will build one model which is similar to this. Obviously, when you are building models for these type of systems, it will not be a simple model like linear or logistic regression or decision tree. It has to be a very complex model which finds out all the patterns in the data, something like boosted model or random forest model. Okay. So this data set has been shared by Auto Group, e-commerce company in US. Their problem statement is slightly different. Every year in their shipyard, they receive, in their containers, they receive a lot of boxes of different type, different style, different shape. They receive a lot of parcels. Okay. Now inside a box, there can be a TV. Inside a box, there can be a laptop. Inside some other box, there can be a mobile phone. Inside another box, there can be a camera. So here the problem statement that they're giving us is every box comes with 100 specifications. Spec 1, spec 2, spec 3, and so on, spec 100. For example, height of the box, width of the box, length of the box, weight of the box, is it marked as fragile or not, etc., etc. 100 specifications. With all these specifications, the item category that can be seen in the box is laptop. Specifications, with all these specifications, the item category is TV. All these specifications, the item category is mobile phone. That's the data that they have right now. What do they want to do? They want to build a model on this data. Next time, when these specifications are given, automatically our model has to predict whether it is going to be a laptop or a TV or a mobile phone or a camera, etc. We can deploy that model on a conveyor belt. As soon as the product comes, we take all these 100 specifications and make a prediction. And let's say this is TV, push it to TV containers. This is laptop, push it to laptop container, etc. I think when you are checking in an airport, have you seen that machine where you have to put your bag on a belt and then that will be checked by the security guards? And have you ever seen that screen? Automatically on the screen, they will see that, okay, this is predicted as laptop, this is predicted as a belt, this is predicted as wallet, this is predicted as mobile phone. Sometimes in their model, there are some items that are not part of the model. Then what will they get? They get some doubt. They ask you to come and open your bag and show it. They confirm it. Then only they send you. If you have to build a similar model like this, what will be our approach? Let us see. Have you understood the problem statement, all of you?
Yes, sir.
Yeah.
Yes, sir.
So basically, based on the product specifications, maximum specifications that we will take, we want to predict what's the product is or what's the item is. This is actually a real data set. This was also run as a Kaggle competition some time back by Auto Group. The challenge name was Auto Group Product Classification Challenge. And look at the prize money, almost like 7 or 8 lakhs, which is not a small amount. Imagine even if you're spending 1 month on it, it's going to be very worthy. But it's not that easy to win the challenges here, but we can always participate. I have given you some idea on Auto Group. They are in USA, Germany, and France, etc. So what they're saying is the item can be washing machine or a sandal or a TV or an apparel. We have to make a classification, class 1 or class 2 or class 3 or class 4 or class 5. So the first impression that we get, what is it? The first impression, is this a binary classification or multi-class classification? In the target variable, do we have 2 values or multiple values?
So multiple values.
Multiple values are there, multiple classes are there. Let's get the data and start importing it and looking at the results. So let's go to the code file, all of you. Give me the code file link. Let's import the packages that are required. It says the notebook requires high RAM. We'll say, okay, no problem. Get the train and test data. Along with me, you're also doing it, isn't it? While we are discussing it, try to execute along with me. Okay, train and test data. Have a look at the train and test data, some of the sample records. Spec 1 to spec 100, specification 1 to specification 100. And then the item category. Target variable is item category. It can be a laptop or a camera or a tablet or a personal care or an accessory. There are 9 types of items. So if you want to look at what are the different categories of items, it can be a tablet or a personal care item, appliances. It can be a laptop. It can be a camera, accessory, iPod, TV, mobile phone. It can be any one of these 9 categories. So obviously it's a multi-class classification problem. We prepare the features. What are the features? Spec 1 to spec 100, specification 1 to specification 100. Usually for this type of model building, when there is a complexity like this, 9 classes in the output, so much of data, hundreds of columns, do you think simple models like decision tree, logistic regression will work effectively on this? Do they give good accuracy on this? There's a very, very less chance, isn't it? Usually they may not give that much accuracy, but I still build them because I want to get an idea what's the basic benchmark accuracy that we generally get. So decision tree model is what I'm trying to build just to get an idea. This is a kind of new output that I'm getting. That's nice. And then the accuracy on the train data is 63%. The accuracy on the test data is 62%. Do you think the accuracy of 63, 62 sufficient for building a model like this in an application like this?
No, sir.
What
No,
will
it's
happen
very
if
good.
somebody orders a mobile phone? What is the chance that he will get only mobile phone? 63%. 62%. And what's the chance that he may get some other item? 40%. That is too high, isn't it? It has to be as less as possible. Obviously, auto group will not do the product classification and directly send them. They may employ human beings and human resources on top of it. Initial classification they should do with this. 100% relying on a model like this is not that suggested, isn't it? You still need some of the human resources. Basic sorting can be done by this model. So directly we can go to XGB package, but just for the comparison sake, even though you're not going to use GBM package in future, you will be using XGB package, but still we will try to build using GBM package. So boosted model using GBM package. We are running it for 100 iterations. Learning rate is 0.1. Verbose equal to 1 means iteration by iteration, the results will be shown to you. Verbose equal to 0 means final result only will be shown to you. This is not a very important parameter. You can ignore that. Now at the end of every iteration, training loss, some kind of error that is shown to us, and the remaining time to complete the rest of the iterations are also shown. So iteration by iteration, we get to see the error remaining, and then what is the time remaining. Now, after 10 iterations, every 10th iteration result is shown. Let's say right now 20 iterations are over. Once 30 iterations are over, you will see the output. Now 31, 32, 33, they're all going on. Okay. Once 40 iterations are completed, whatever is the loss means some kind of error that is internally calculated using some formula. Whatever is that error that is shown to you, and this is the time that is remaining for completion. So we have running it like we have set it for 100 iterations. So for me, nearly 50 iterations are over. 50 more iterations are going to execute, and the remaining time that it takes is roughly around 1 more minute. Looks like overall 3 minutes is the time for executing all the 100 iterations. What happens is it takes 3 minutes for model building. But if I'm doing for model prediction, let's say to create confusion matrix, you need model predictions, isn't it? Prediction doesn't take that much time. Model building only takes time here. When you're using that model, you're not building anything, you're not creating anything. So right now 70 iterations are over. 30 more iterations to go. Last 20 iteration, you can also keep it executing. Hundred iterations over around 166 seconds, which is like roughly 3 minutes. Model building took 3 minutes, but when you try to predict it, it doesn't take 3 minutes, fraction of second. 80% accuracy on trained data, almost 78.8, 79% accuracy on the test data. Look at this, model prediction did not take time. That means while building, you can take any amount of time, while when you're deploying it, model will be predicting quickly because there is no learning over there. That's the GBM package, but usually it's not the GBM package that you will use. It's the XGB package that you will be using. Once again, I'll explain the parameters in XGB. But before that, let's make sure that everybody is done with GBM package. Give me a message once you're done with this GBM results, then let me know. Run. Okay. Let us look at XGB package. What XGB package tells you is you cannot give a pandas data frame as input. You have to convert it into a matrix format. So this is kind of standard step. These steps you have to do it for sure when you're working on XGB model. Okay. Basically converting into a matrix because XGB expects our input to be in matrix format. Here comes the parameters. Look at the parameters. The first parameter is max depth. It is suggested that you have to build shorter trees. If you build shorter trees, what happens is the algorithm will prolong, and prolonging the algorithm is very important. Why? You will be able to find the fine granular point. So you have to prolong the algorithm. You have to build shorter trees. Suggested ballpark number is you look at your original decision tree model, whatever its depth, take almost half of that. In our original decision tree model, the depth was 9. So we are taking somewhere around 9/2 around that. So that is around 4 or 5. You can take the depth as 4 or 5 here. ETA stands for learning rate. What is the standard learning rate that we tend to give? 0.1. If that is not working, usually that works. If that is not working, what's the range that you can try? 0.0001 to 0.1. Anyway, it's not a sharp point that you have to pick it correctly. Anywhere in this range, usually it works. The third parameter is evaluation metric. Some kind of error is calculated and shown to us. This error is not that easy to interpret. Okay. So what do? We tend to change that to multi-class classification error. Simply it's the error. Let's say for us error 20% means 80% accuracy. Error 25% means 75% accuracy. So instead of showing that training loss, try to show us the error. That's the difference here. So in the output, you will see the error being displayed to you. Tree method is equal to GPU hist. What does this option do? It will search for the GPU in your system. If there is GPU, then parallel processing will happen. Everything will happen much, much faster. If there's no GPU, this command will be ignored. In Google Colab runtime type, if we check that, GPU is already given to us. Okay. Some part of GPU is given to us. You don't need to do anything here. So it will automatically consider GPU. Number of classes. This parameter is number of classes in the output variable. We have 9 classes. 1, 2, 3, 4, 5, 6, 7, 8, 9 classes are there in our output variable that is given here. Okay. These are the parameters. Okay, in boosting. And what are the remaining one? Once you give all these parameters, you say model equal to XGBoost dot train. Take all those parameters. Take my training data matrix. Number of boosting rounds. These are the number of iterations. I'm running for 300 iterations. What happens if you're running for too many iterations?
So the replication of data will happen.
Isn't it? If we are running for too many iterations, it may generally lead to, usually that will definitely lead to overfitting. So that is why to avoid overfitting, we can use this option early stopping rounds equal to 4. What effect that early stopping rounds will have on the final result? For example, we have mentioned the number of iterations equal to 300. So on the train data, if you see, you start with first iteration, then second, third, and so on 50 iterations, and so on 100 iterations, and so on 200 iterations, and so on 300 iterations. The accuracy on train data keeps on increasing. Iteration by iteration, the accuracy on train data keeps on increasing. One day, the accuracy can be 100% also. Is it possible to have 100% accuracy on train data? Does that happen? Train data has 100% accuracy. It can happen because the model is looking at the train data. However, test data accuracy, initially it may increase. Maybe it increased. Let's say until 75 iterations, the test data accuracy increased. In the 76th iteration, the test data accuracy decreased. Okay, we think that it is just an aberration. Let's proceed. Again, it decreased 77th. Okay, let's proceed. 78th iteration also it decreased. 79th iteration, 4 consecutive times the accuracy decreased. Do you want me to proceed further? Do you want me to stop early at 75th iteration itself? 4 consecutive iterations, the accuracy decreased. Is it smart to proceed? What zone are we entering? If we proceed further, what will happen? Definitely we are entering the zone of
Overfitting.
Overfitting. So stop early at 75th iteration, which means no matter how many iterations you are giving, is there a guarantee that these many iterations definitely will be executed?
No, sir.
Those many iterations will not be executed because the moment this XGB sees that 4 consecutive times the error did not reduce, 4 consecutive times the accuracy actually reduced, then it will stop early. This is a very good option. So you can give any number here, give early stopping rounds equal to 4, stop after 4 rounds if the error doesn't improve. So with this matrix formation, with these parameters, if you give this, if your GPU is working, it will work much, much faster. And it took how many seconds? 2 seconds. Earlier, this used to be a very big difference. Earlier GBM, like imagine GBM is taking 6 hours, XGB with GPU is taking like 5 minutes. That used to look very, very different. Now, though it is like 160 versus 1.7, almost it's 100 times faster. Yes or no? Though it is 100 times faster, we don't feel the real pace of it because anyway, that is also a smaller number. 3 minutes versus 1.7 seconds doesn't matter. That's why people don't really care whether you're using that package or this package. In terms of accuracy, which one will be more accurate? Is it GBM or is it XGB? Which package will
GBM,
give you
sir.
more accuracy?
GBM.
Since both the packages use the same theory, If two packages are using the same theory, but the code that was written is different, will there be a difference in the accuracy? Think of it.
Really, not really.
There should not be any difference, isn't it? GBM package works on boosting theory only. XGB package works on what? Boosting theory only. So in terms of accuracy, you cannot expect a very big difference. There will be a difference only in terms of the overall execution time. Okay. So basically, if you are giving the right numbers here, that means once you give the parameters that were similar to the previous one, the accuracy that you get here would be same as the accuracy that you get there. Okay. Actually, these parameters are kind of, we just picked them. If you spend some time in fine tuning them, okay, then you will one day you will definitely, or after a few iterations, you will definitely reach to a place where the accuracy on this one will be same as the previous one. Okay, so let us try different ETA 0.1, and then maybe if you try depth of 5. Let us see, the accuracy is 81% on trained data, 79%. But you should not see this 81% is very different from this 80% and so on. Like maybe if you again fine tune, tweak some of the parameters here. So overall, since they both of them are working on the same parameter in the backend, same theory in the backend, so difference in accuracy will not be much. It will be the same. But execution speed is very, very different. Execution speed, XGB with GPU is much, much faster. Got it? That is the story of GBM or the boosting. In the interviews, let's say if you're saying that I have built a credit risk model, can you explain GBM and random forest? They are the methods that are used for building a credit risk model. Does that
No, sir.
happen? No, we cannot
No,
do that,
sir.
isn't it? Why we cannot say that random forest and boosting was used for building the risk model?
The
Sir, the
black box.
interpretation is difficult.
And because in real world that doesn't happen. But still we will do this just to get an idea on the working procedure of GBM and all that. But keep that in mind, like you have to say that I have used it in a different place, or in marketing you can say that. You can say that in random forest and boosting has been used for marketing models, but for risk models, it's only logistic regression that we can use. Okay.